You can say that on, I thought you said that on Friday, a group meeting.
I just said that the other postdocs aren't going to be here, so the attendance is probably going to be bad. Sorry, I didn't mean to imply that it was cancelled.
It's okay, I made it. Anyway, sorry for disrupting.
Oh no, I haven't started yet. So, hi everybody, I'm Saraswathi. I'm a new postdoc here. So I'm going to be talking about daytime turbulence, strength profile measurements, and other parameter measurements that I did as a part of my PhD back in India. So just with a little bit of background, so NLST is the National Large Solar Telescope, which is a 50-meter class solar telescope that is supposed to come up at Merak, and the median seeing there is about 2.3 arc seconds, which means you do need AO for your observations. And it's slightly different from maybe what you guys are used to here. The sun is obviously an extended source. The full disk image is half a degree. And so we would prefer to go for something like MCAO because you want to have AO correction over a wider field of view. And the most important parameter for in the design of an MCAO system is finding out to what height you want to conjugate your this telescope is not built yet. So we mostly worked with a 38 centimeter telescope at the Kodaikanal Observatory. And there had been no CN square measurements at Kodaikanal until then. So the goal was to basically get CN square measurements and also other parameters of the turbulence itself. So this is just the schematic of the telescope. So we have
CN squared measurements.
I'll come to that.
Okay.
Okay. Yeah. So there's a 2-meter cirrostat that's mounted about 11 meters off the ground because during the daytime, one of the main things is that the ground heats up because of sunlight, and that generates a lot of turbulence. So you usually have the telescope on a tower, and then so the rest of the telescope is technically underground. So M3 directs the light into this tunnel where an achromatic doublet actually brings it to a focus. And this has a 26-meter focal length, which means that your plate scale is actually huge at the prime focus. And the full disk image of the sun is actually 34 centimeters. So this is literally me holding a piece of paper at the focal plane, and you can see a sunspot, you can see the umbra and penumbra there. So yeah. Maybe I'll come to that in the next slide. So we considered 3 different techniques to measure the CN square profile. The classic sort of balloon-borne temperature sensors, and S-DIMM plus and SHWFS are optical methods where S-DIMM plus is basically just an extension of the DIMM where you use image motion measurements, and SHWFS, it uses scintillation measurements to get to the CN square. So the problem with optical methods is that when you're studying the light from not just the sun, but any source for that matter, basically if you trace the wavefronts coming from your source to the telescope, as you increase in height, you're actually sampling a larger area of the atmosphere, which means your sensitivity starts to go down as a function of height. The advantage of S-DIMM plus is that you place it at the telescope focal plane itself, which means you're seeing the turbulence profile as seen from the telescope, whereas the other 2 instruments are slightly displaced. So then you have to think about the effect of other local features at your site. And the first 2 were also just easier to implement, so we decided to go with the first 2. So coming to CN square, it's basically the refractive index. It's a measure of the strength of turbulence and how it varies as a function of height. And one way to do it is to get to CN square from temperature fluctuations, where you measure the temperature structure function, which is Tt of R. And in principle, you just need 2 temperature sensors to measure the fluctuations in temperature between 2 points that are separated by some distance. And then you need some mechanism to displace this as a function of height. And from Dt, you can then get to CN square. So we actually went with 7 PT100 sensors that we mounted on a rod, and we chose the separations between these 7 so that we had all possible separations from 10 centimeter to 110 centimeter in steps of 10 centimeter, and we also had some redundant baselines. We were not able to launch the balloon because of where the site was. It's surrounded by this forest land and it was difficult to get permission to launch it. So we went with like a tethered balloon. So we literally had like a rope holding the balloon and that was had markings every 10 meters. So essentially we were measuring the temperatures at every 10 meter. Yeah, so the calibration is because yeah. So basically the PT100 sensor, it changes its resistance based on the temperature that it senses. So, and what we get from the electronics is obviously just your ADC counts. So we first connected known resistances in the place of PT100 so that we could go from counts to resistance. And then the PT100 has this standard relationship to go from resistance to temperature. So that was the calibration for the instrument. And we were quite lucky on the days that we went for observation. There's very minimal wind, so our balloon was actually quite straight up, and we were able to go up to 350 meters. And this is one of the data sets that we recorded. And the Hafnagel Valley is a sort of well-known CN square model, but it has this one component for just the nearer turbulence for the daytime. So we tried to fit it to that. It's not a great match, but we could see like the rough trend of the profile. And
Sorry.
yeah.
I was gonna say, what time of day was this measured?
It was before noon. Yeah.
So you tried to do it at roughly the same time as when observation. So
yes,
like
yeah.
decast, right? A lot of them start as soon as the sun's coming on the horizon.
Yeah, so we had two going on simultaneously. We had the balloon, and then we also had the S-DIMM inside the telescope near simultaneously, and we did see the seeing degrade as a function of day as well. So for this one, we weren't able to do it afternoon because it became really windy, so we weren't able to hold the balloon up basically. And yeah, but the other one we were able to do it, and we saw that it degraded as a function of day.
It's the same page.
Sorry?
The same page.
Here?
Yes. So have you compared with the horizon line fitting?
The what fitting?
So like this, if you only see the data, it looks like just a horizon line.
Yeah, there were some, so this was just one of the data sets. So yeah, it was a rough match. It was not a great match. And there were some approximations that went into our system. So that's why we think it was like a first level result, but there is scope for improvement to change the electronics and then repeat it. And we think that will improve yeah.
Were you surprised not to see a boundary layer?
We're already 11 meters above that's why the primary mirror is 11 meters above the ground. So we think that the boundary layer is between there. So yeah.
May I know the error source?
Sorry?
The source of the error.
Okay, so one thing is that we went actually with a serial readout thing because we wanted it to be easier for calibration. Ideally, it's better if you do it parallelly. So there's actually a time difference between the data recorded by the different sensors. So you're not actually measuring the difference in fluctuations at one instant of time. So that's one potential source of error that we have. Yeah, and also another thing is that this is technically not CN square of H, it's CN square of H comma T because it takes some time. Yeah, there's a temporal component as well because you're moving the balloon in height and that takes some time. So you're not actually measuring the profile at one instant of time. The whole experiment in the ascent and descent phases took us about 2.5 to 3 hours. So it's a profile as a function of time as well. And you will have temporal evolution of the turbulence also. So yeah, but that's just an intrinsic property of how this method works. So you can never beat that temporal factor. Yeah. Okay, and the S-DIMM, which is just the solar DIMM, is an instrument that's usually used to measure R0 from image motion estimates. And the idea is that you use two apertures on a common mount, and they produce two images of the same object. And you take the differential image motion of these two images to get to the R0. And the differential is important because the absolute image motion would have the contribution from the atmosphere, but it would also have it from, say, like your telescope vibration and things like that. So you remove the instrumental sources by measuring the differential image motion. So extending it, okay, I would just like to apologize for my animations. They're a little crude. So yeah, the S-DIMM plus, what you do is instead of just having two subapertures, you have multiple subapertures. You can do that by having a Shack-Hartman at your reimage pupil plane, and each one produces an image of the solar region. And
Sorry. You have a Shack-Hartman in your DIMM?
in my S-DIMM plus, so it's,
So,
yeah.
So it's. Sorry, I'm trying to understand. So in a traditional DIMM,
Hmm.
does everyone know what a DIMM, is everyone familiar with these?
No. I've heard of
I should maybe then.
Give
Okay.
DIMM 101.
So basically, you could, in principle, just use like an aperture mask on your pupil, and you have, two apertures, and then you produce, let's say you just take a star, and then you observe the same star through both these apertures. So you have two images at the same time, and then both of them will have image motion, and then you estimate the the longitudinal and transverse, which is basically the image motion along the line joining these two subapertures and perpendicular to the line joining these two subapertures. And then so that you can get from your experiment, the wavelength of observation. S and D are again your subaperture diameters and separations, and you can basically get R0, which is your Fried's parameter.
Yeah, the other thing we mentioned is that it's not just two holes.
Yeah.
Actually, one has a like a prism or a wedge.
Yeah, so that you have two
So
images.
that you get two PSFs.
Yeah.
Yeah.
the idea
Yeah, that's
is
where
that
I was getting-
telescope-
Okay.
If your telescope has a bulk motion from wind or whatever, they both move,
Yeah,
right? Whereas if it's a turbulence thing, then you get relative motion of both.
yes.
So. Okay, so you can't just point this at the sun though, because, well, I don't know, you tell me. Normally, if you start with a point source, this traditional DIMM reimages your point sources. If
Yeah,
you're pointing this at the sun,
Hmm.
that's a resolved object,
Hmm.
you get two images of the sun.
yes.
That's harder to centroid on, or is that?
Oh, you don't use centroiding. You have different algorithms for estimating the image motion. Yeah, so the two sort of main ones that at least we tested, one is called sum of absolute differences, where you have a, say, n by n image. So you have two images. So the thing is, you always need like a reference image, right? So yeah, so you always find the image motion of, say, image 2 with respect to image 1. And if you have, let's say, n by n image, then you choose the central m by m of the second image, and you literally slide it across the first image. Sorry?
It's like a correlation basically.
Yeah, so you can do it in the Fourier plane also. So if you do it in the image plane, then you literally just find the difference, pixel to pixel difference, find the sum. And when they match exactly, your sum is going to be minimum. So you just repeat that. So that's one. And then in the Fourier, you do like a correlation, and then it'll give you a peak corresponding to the shift. So
Is one faster than the other?
it depends on the image size and your typical seeing. So when you go for larger image sizes, the Fourier method is faster. But the problem is that if, let's say you have an n by n window, then you can only have image motion measurements plus or minus n by 2. Actually, it's slightly less than plus or minus n by 2 because when you do the Fourier transform, you also multiply it by your windowing function. So you lose some in the sort of roll-off area. Whereas in the image plane, sum of absolute difference is 1. So even if you have an m by m window that you're sliding across, you can move beyond the m by m. So you can change the resolution of your maximum, not the resolution, the maximum image motion estimate you can get. But
Range of the algorithms.
yeah, but it's slower, especially for larger arrays. So usually what you can, so this gives you an idea of, if you know the typical R0 values at your site, and you know the size of your subapertures and the distance between them, you know what values of image motion you can expect. And then from there, you can decide which is the better algorithm for you. But there are times when the seeing becomes very bad, where you will underestimate the image motion. Yeah. Okay. Yeah. So here, you have, like I said, a Shack-Hartman in your pupil plane. And so basically what happens is that each of these produces an image of the same field of the sun, which are ideally supposed to be identical, but they're going to be shifted because of the turbulence. And the idea is that the wavefronts emitted from these different field regions, which is what the red, white, and black circles are, they traverse different volumes of the atmosphere before they reach your, different lenslets of your Shack-Hartman, right? So essentially by cross-correlating these field, the image motion of these field regions, you are actually sampling different heights in the atmosphere. So that's like the theory. So here we build the longitudinal and transverse covariance matrices from the image motion estimates. And these are basically a function of which two, say lenslets you're choosing in the pupil plane, and then which two field regions of those two lenslets that you're choosing in the image plane. So by changing the combination of these two, you can build this matrix. And then fx and fy are basically just like these theoretical functions which come from the image motion estimates, and you can find them when you know your like system parameters, and then it becomes a matter of just fitting for the CN coefficients, which gives us the R0 values at different heights. So you get to the CN square that way. So this was.
So this is meant to be. Sorry, I was understanding. So you take your pupil, re-image it to something smaller, pass that through a lenslet array. So it's kind of like a mass in some ways. It's a mass. Like with the mass.
Oh, yes.
Yeah, okay. So it's like an analog of the mass.
Yeah.
But instead of cutting up into cylinders and pitching them to different. Okay.
Yeah.
Okay. So, and does this go back? This is something small that you put on the back of the.
Yeah, there's a
30-centimeter telescope.
It's 38. We reduced the aperture to 36. Yeah, but then that's that. So basically we have, so the thing with okay, maybe I forgot to say this one. So the achromatic doublet is what brings it to a focus here. And this is mounted on a rail, so we can move it back and forth actually. And we just have a lot of space here to place our instrument, which is very small. That's just it. Yeah. I'll come to that. Yeah, so one of the things that we had to, okay, these small field regions are what we use for finding the image motion estimates and then to build our covariance matrices. And one of the parameters that we needed to fix was finding what size would be best for our telescope and for our site parameters. Because S-DIMM Plus has mostly been, at least before we did it, it was done with 1 meter or larger telescopes. And with a smaller telescope, you do expect the magnitude of image motion to be higher, and our sight is also not great. So again, more image motion. And like I said, what algorithm you choose basically fixes the accuracy of your image motion calculation. So we needed to fix those parameters. And also, let's say you're given a set of lenslet array images like as a function of time, then how do we actually, get the covariance matrices and then get to the turbulence strength profile and what would be the best height grid for our system? So we did the simulations for this, and we started with simulated solar images. So there's another group that do like MHD simulation. So they gave us this, and this was the closest you can get to like a true object without any residual instrumental or atmospheric, response. And we had multi-layer atmospheric turbulence, and then these are just like our system parameters. So we get a series of lenslet array images as we would get from our experiment. And we found that having 13.2 arcsecond by 13.2 arcsecond field of view, which is actually quite large because other experiments were able to use like a 5.5 by 5.5 arcsecond field of view for their image motion estimates. And then do basically an ensemble average across 200 frames. Yeah. And for then what we did was we first didn't start with like a multi-layer model. We started with like a single layer of turbulence at different heights. And then we gave the input and then we saw if our code was able to retrieve it back. And then we increased it to like 2 layers, 3 layers. And eventually we ended up with a 6-layer model. And like I said, one of the sort of properties of this method is that your sensitivity goes down as a function of height. So we see that at the 6 kilometer layer, our sensitivity is poor. And the thing is, we were underestimating the turbulence, at the higher heights. But the thing is, we're not interested in the absolute strength of turbulence. We only wanted the relative strengths. So we just wanted to be able to identify the strongest layer. And we were able to do that. So we were satisfied. So this was the setup. So we had like a field stop to choose a 20 by 23 arcsecond field of view, which would go into the Shack-Hartman, and then just re-image that. And the polarizer analyzer combination was used just to reduce the intensity of light. And we recorded data at 540 and also at H alpha. So that was the wavelength filter, and then a Shack-Hartman and a camera. So the interesting thing here is that this was done in like Jan 16, 17, 18, around that time. So the sun was very close to the southern limit. I think the declination was like -20 or something. So when we first started observations, we got what's at the top here. It's with the same setup. But basically what was happening was we had pushed the mirror, the primary mirror to the edge of the mount, and it was not properly illuminated. So you see the effect of the partial illumination of the primary at your re-image pupil also. And then so basically that's just the image motion. And another thing is that actually the 8 a.m. images are sharper compared to the 11:30 a.m. images, which again, because of the heating of the ground. At least at 11:30, this was somewhat better, but post-noon, it just started degrading even more. So yeah. So we see that, in the before noon and the afternoon profiles, there's like an order of magnitude difference in the CN square itself. So, and our inversions just started failing in the post-noon curves because the turbulence had degraded so badly. And in the pre-noon curves, we have 2 layers, one at 1 kilometer and one at 3 kilometers. So that's where we can conjugate the second deformable mirror of our MCAO system. So the other thing that we explored was if we could estimate other turbulence parameters apart from the CN square profile.
So how many times did you do this? Because how many times did you do this measurement?
This was across 3 days, and each data here is actually about 2,000 frames of data.
So is there a reason to
10
think
sets
those
of two.
layers-
Sorry?
Is there a reason to think that your primary turbulence layers are going to vary throughout the year?
Yeah, we do want to repeat it. It should. Yeah, there is a seasonal. Usually there is a seasonal component as well. So yeah, it's not a statistically significant result. It's a result. Yeah. Yeah. So okay, maybe I should have. Is everyone familiar with the isoplanatic angle? Okay. So usually we use deconvolution to remove, say, the instrumental response of your system and get back to an estimate of the true object or to improve your contrast. But the thing in ground-based imaging is that you have your PSF, it contains of course the instrumental response, but there's also an imprint of the atmosphere in any ground-based image that you take, which means you can now use deconvolution as a tool to probe the atmosphere. And for seeing limited long exposure images, the contribution from the atmosphere has this like well-known analytical form where it just depends on R naught or the Fries parameter. So this was a method that was already developed. It's called the parametric search method, where they use deconvolution on long exposure seeing limited images of the sun to estimate the Fries parameter or R naught. So you essentially choose a small region of your solar image, and then you deconvolve it with this transfer function corresponding to some value of R naught. And then you estimate the contrast, and then you change the value of R naught and then deconvolve it again, and you get an estimate of the contrast for basically by varying R naught. And when you fit two straight lines to the ends of the curve, the point of intersection gives you an estimate of the R naught. And the question we wanted to ask is if we can exploit the extended nature of our source to estimate more information about the characteristics of the turbulence at our site. So this is what the PSM did, right? So it chose an image and then got an estimate of R naught. So if you increase the size of the image that you're using, what you're basically doing is sampling a different volume of the atmosphere, and you keep doing this iteratively, and then you're again essentially sampling different volumes of the atmosphere, and you're building like a map of R naught as a function of field of view. And this was done with the 20 centimeter telescope at Merak. The images were taken at H alpha, and we see that the R naught starts to go down when the field of view of the image that you're using for deconvolution increases. And this is sort of expected because when you basically increase the field of view, you're actually sampling more of the turbulence, and that gives you this decrease in R naught. And the other interesting thing is that so this spread in this plot is because of the different images taken during a day. So if you plot it as a function of time, the R naught is almost constant as a function of day. And this is because Merak is a lake site. So there's like a lake right next to the telescope. And that is preferred for solar telescopes because water heats up more slowly, which means that your seeing is more consistent throughout the day. So yeah, we just did that for like more data, and that's what we found consistently. So thank you.
So sort of deconvolution, so like deconvolution's considered kind of dangerous in non-solar astronomy. But so I'm kind of wondering, do you use it in solar astronomy because you have to, because you don't have like isolated point sources?
Yeah.
That's basically it. So
Yeah.
You're forced
Yes.
into, okay. Yeah, I guess because there's no, yeah, because you don't have a source small enough on the sun, yeah.
It's very hard to get the PSF during the daytime.
Yeah.
Yeah.
Sure.
And some people, some people do sort of work around it by observing at night, but your turbulence is different. So it's like, it's not the same PSF. So, yeah.
Yeah.
So it is very hard to get the PSF during the daytime.
So weird, like solar astronomy compared to nighttime astronomy, like you think they're the same.
They're not.
There's so many things we just like take for granted as easy. Don't get to do in solar astronomy. Cool,
That was quick.
thank you. Sorry, I know I interrupted you right on your thank you slide.
Oh, that's okay. Thank you.
No. Okay.
What is it, sorry, what is H alpha, the wavelength?
Just the wavelength.
600 nanometers-ish?
656.3.
650, okay, I was like, I knew it's around 600-ish, but I forget.
Okay. Maybe I should give more context. Sorry.
Sorry, so you did this using the telescope because you don't have an instrument on the back of it right now, another instrument on the back, or how does this work?
This one.
Yeah, you put that for this measurement, right? Is it there all the time being used? Like, do you
Oh, this
swap it
one,
in
yeah.
and out, or what's
This, so at most solar observatories, you do have a small 20, 30 centimeter telescope observing usually the full disk regularly. They just keep monitoring the sun and taking images at low resolution.
But this one you used. Oh, okay, so
It's
sorry.
the first was a different telescope. This is a different, yeah.
Okay.
So that one actually no one uses, so we just use it for experiments right now. There is a spectrograph also at the back end, but they do, but then when we go, we just like interrupt them and take the data. Sorry.
So I think I missed the motivation part because I walked on a little late. But what is it about the sun that you are trying to learn? Like,
Oh,
I
there are
completely missed that.
so many things that they still don't know about the sun. So the goal is to get higher resolution images from the ground, preferably. And if you want to study, say, sunspots or things, they usually pick features. So so there is an upcoming 2-meter class solar telescope. And then one of the backend instruments for that is an imager which has a field of view of about 1.5 arc minutes. So you want AO correction over a wide field of view, for which you need MCAO, for which you need to know your turbulence profile distribution at your site, so that you can determine the height to which your second deformable mirror needs to be conjugate. The first one will always be conjugate to pupil. The second one you conjugate, it's better if you conjugate it to the layer that has the highest turbulence strength, because then you have a better correction. Some observatories, what they do is they don't do the CN square measurements, they skip it, and they essentially have the setup slightly more complicated, where they have a bunch of mirrors, and then you can sort of dynamically change what height the DM is conjugate to.
Like shift the.
Yeah, you have
Okay,
everything.
so-
Yeah. So, and then you have the mirrors, like it's sort of like a Z configuration, so that when you basically change the distances between them, you're changing the altitude to which your DM is conjugate. But it's also really tricky aligning so many components, because you don't have a point source. You're working with an extended source. So it's easier to fix a height and have a simpler setup.
I have maybe still big questions. So why can't we just send a spacecraft with a telescope to the sun?
It's more expensive. Yeah.
I thought that as well.
Yeah.
It's stupid. Has a
There have
solar
been-
telescope in space been proposed?
There are so many.
Okay.
There's like a whole bunch.
Yeah,
Wait, I think I
solar
should.
astronomy is like, we never talk about it, but it is huge. Like, they have buckets of funding and buckets of,
Isn't there currently one?
There are so many.
yeah.
But
I'm so glad I have my
is there
thesis.
anyone? Is there any one of them fly by?
Oh yeah, Parker Solar Probe, yeah, is the closest right now.
The Parker,
The closest one is Parker.
Yeah.
There's like a whole host of instruments.
Yeah.
And so, like, how big are those solar telescopes?
Not too big,
I was-
yeah.
Like their aperture's probably. like this
Well,
big.
don't forget, you get massive thermal problems.
Yeah.
Yeah.
With the sun, right?
Yeah.
So DKIST is a 4-meter on the Ottawa, and a good friend of mine is the control engineer there. And a whole bunch of the telescope, like one of the biggest problems is actually when you have the primary that goes into the secondary, and the secondary is like yay big. When you think about the amount of heat that goes into the secondary, one of the biggest engineering challenges of the telescope is not melting M2. And just getting the heat out of it, basically.
Which is why we have a 36-meter focal length. So 36 meters is like about 120 feet. So it's a long tunnel that you go inside. Yeah. Again, this is quite an old telescope, which is why this was what was done. But now we have more sophisticated means of dissipating the heat. You have like heat stops and things. Because what you're doing here is you're generating internal turbulence by having such a long focal length. So
Kid Peak has one of these. Kid Peak has these.
it's the biggest, I think. So this is the full disk image size is 34 centimeters. I think there is like 100 centimeters or something. Yeah.
I'm not sure.
And back then you also had like photographic plates. So detectors were not a problem for, like a 34-centimeter detector.
You can do like special coding designs now on your full aperture, so you don't just blow out your secondary.
Well, not really, because you still focus all the wavelengths.
But if you somehow had like a broadband coding that was like really low reflectance,
But that means it's high absorption. So that means the energy is,
it could be transmission. You did like a no metal on your mirror and let it be a window.
it
that
gets
reflects-
absorbed, it has to get absorbed somewhere.
Sure.
So for solar astronomy, is it like the goal is like you don't need as big of an aperture because?
If Ramya was here. So for imaging, no. But
Okay.
for spectropolarimetry, especially, they're still photon starved. Yeah. So that's the issue.
Are they trying to like be narrow as possible?
Yeah,
That's why-
yeah. In imaging, you never, that's why we just like literally put a polarized analyzer and we were like we were able to. But if this goes in between, say, if this is like, if the AO system becomes like an intermediate instrument and then you feed it into a spectroscope or a spectropolarimeter, then yes, they do run into problems there.
But I think the resolution, their spectral resolutions they're looking at are
Yeah,
like 100,000 or something.
yeah.
It's not far of 100, like we do.
Yeah,
right?
no.
I think they're a different set of problems.
Yeah, that's crazy, yeah. Super cool.
So you mentioned spectropolarimetry. Is this any intent for putting a magnetograph on this?
Not right now. There is a spectrograph and there's a polarimeter that go. So like I said, so this one is movable, right? So the spectrograph is fixed. The polarimeter was like movable, and then we just put our whatever, not our AO stuff, but our CN square instrument in front of it. Yeah, right now, no. It's being recorded. Okay.
Turbulence is fun. Cool.
No more question, I'll stop recording.